Have you ever really thought about what's going on inside your phone or your TV or, well, anything electronic? It all just boils down to controlling electricity. So today, we're going to pull back the curtain on the four most basic components, the absolute building blocks for pretty much every gadget you own. All right, let's jump in.
I mean, they couldn't seem more different, right? But they all share this little secret. They all run on electricity, of course, but more than that, they all control that electricity using the exact same handful of super simple, universal parts. Today, we're going to see what makes them tick. But hang on, before we can even talk about the components themselves, we've got to get a handle on the three fundamental forces they're built to control. You can think of these as the basic rules of the game for, well, all electronics. First up, we've got voltage. Now, the easiest way to wrap your head around voltage is to just think of it as electrical pressure, kind of like water pressure in a hose. Voltage is the push that gets electrons moving through a wire. So, more voltage means a stronger push. Simple as that. Okay, so if voltage is the pressure, then current is the actual flow. It's the real movement of all those electrons through the wire. When you hear someone talking about how much electricity is moving, they're talking about the current. And we measure that in amperes, or just amps for short. And finally, number 3, resistance. See, every circuit needs a way to control that flow, and that's exactly what resistance does. It's like friction, or maybe a bottleneck in the pipe that puts a limit on how much current can get through for any given amount of pressure. So we have pressure, we have flow, and we have a bottleneck. And what's really amazing is that the relationship between these three things is all tied together by one beautiful, super simple rule: Ohm's law. This is the key. If you get this, you get how basic circuits work. And here's the beautiful logic behind it. If you crank up the pressure, the voltage, you're going to get more flow, more current. They go up and down together. But if you make the bottleneck tighter, increase the resistance, you're going to get less flow. See how that works? One goes up, the other goes down. And this is the math that makes it all work. Voltage equals resistance times current. U equals R times I. It's such a simple formula, but it is the absolute bedrock for figuring out what's happening in a circuit. So burn this one into your brain, because we're about to see it in action. All right, let's meet our first component. This little guy is the resistor, and its entire reason for being is to create that resistance we were just talking about. You can think of it as the most basic, most fundamental gate for electricity.
To really see what it does, let's just do a quick experiment. We're going to hook a resistor up to a power supply and just watch what the current does when we start messing with the voltage.
Okay, first, let's apply just 1 volt of that electrical pressure. Just a little nudge.
And with that 1 volt, we get a nice, steady flow of 22 milliamps. Okay, so that's our starting point. Now, keeping Ohm's law in mind, what do you think's going to happen if we triple that voltage?
Let's find out. We're cranking that pressure all the way up to 3 volts.
And would you look at that, almost exactly 66 milliamps. It's perfect. It's totally proportional, just like Ohm's law said it would be. You triple the voltage, you triple the current. It really is that straightforward.
So the big takeaway here is that a resistor is just a simple, predictable component. The amount of current it lets through is tied directly to the voltage you put across it. And here's something really important. It doesn't care which way the current's flowing. It works the same forwards and backwards. That predictability is why they're in everything, controlling stuff like the brightness of an LED or the volume on your stereo. Okay, so resistors are pretty simple. But what if you want to control electricity in more clever ways? That's where our next two components come in. They're a little more specialized. Now, these next two are a whole different ballgame. In a basic DC circuit, a capacitor doesn't just reduce the current, it actually stops it cold. And a diode? Well, it acts like a one-way street, only letting current go in a single direction. So let's look at the capacitor first. When you apply a steady, direct current, a tiny little bit of current flows for just a split second to charge it up. But after that, nothing. It's a total dead end. It basically acts like a break in the wire, like an open switch. This whole ability to block DC is super important for things like filtering power or tuning radios. Now, on to the diode. The diode is all about direction. If current tries to flow in the direction of its little arrow symbol, no problem. It passes right through. It's like a closed switch. But if that current tries to go the other way, nope. It gets completely blocked. The diode slams the door shut and acts like an open switch. And this is the perfect way to think about it. The best analogy for a diode is a one-way check valve in plumbing. Water can flow through one way, but if it tries to flow backwards, a flap slams shut and stops it. A diode does the exact same thing, but for electricity. And that's literally how your phone charger turns the AC power from your wall into the DC power your battery needs. Pretty clever, huh? Okay, that brings us to our fourth and final basic component, the inductor. Look at it. It's just a coil of wire. It looks like it should be doing something really complicated, right? Well, let's see.
So we've seen components that reduce current, block current, and direct current. What kind of special trick does this fancy coil of wire have up its sleeve when we hook it up to a steady DC power source?
And the answer, believe it or not, is absolutely nothing. Yeah, for a steady, unchanging DC current, an inductor might as well just be a plain old piece of wire. It has almost zero resistance. It just lets the current flow right on through. The real magic of an inductor, its whole purpose, only shows up when the current is changing. It hates change. And that property is what makes it so critical for things like power supplies and transformers. So let's do a super quick recap. For a simple, steady DC circuit, a resistor just reduces the flow. A capacitor stops it dead. A diode is a one-way gate. And an inductor? It just acts like a piece of wire. Think of this as your little cheat sheet for the 4 basic behaviors.
So we've seen how these guys behave when everything is stable and steady. But the really fascinating part, the part where capacitors and inductors really show their true colors, is in that split second when things are changing. Right at the exact moment you flip a switch. What happens then? Well, that dynamic behavior, that's what makes all of modern electronics possible.